Hey everyone, welcome to This Explainer. Today, we're diving straight into a fascinating look at the invisible mechanical problem solvers that literally keep our world turning. From the delicate ticking inside a precision wristwatch all the way up to the massive, roaring thrust of a commercial jet engine, the applied uses of mechanical gears act as the hidden muscles of modern engineering. They're everywhere, they're constantly working, and yet they're rarely seen.
Here's our roadmap for today. We're going to cover 1. The power of gears. 2. Controlling speed and torque. 3. Driving cars and ships. 4. Aerospace and renewable energy. And finally, 5. Microrobotics and surgical tech.
Okay, let's dive right into this with Section 1. The power of gears, the invisible forces powering our world.
So at its absolute core, a gear is just a mechanical component with evenly spaced teeth. And when two of these mesh together, those teeth interlock to seamlessly transfer motion, torque, and power right between rotating shafts. I know, it sounds super simple, right? But it's this exact interaction that makes it possible for us to precisely control rotational speed and completely redirect motion across entirely different axes.
And this brilliantly illustrates the physics in action. Check out that specific geometric tooth profile. It's an involute curve. It's perfectly designed so that when the teeth actually mesh, they make contact at one very specific location called the pitch point. That single tiny point of engagement is what dictates the exact velocity ratio between the two gears. So we're not just talking about metal clumsily bumping into metal here, it's literally a mathematically perfect transfer of kinetic energy.
Moving right along to Section 2, Controlling Speed and Torque, the Fundamental Mechanical Trade-off.
Now, here's the fundamental problem gears are built to solve. When a massive gear drives a smaller one, your output speed shoots way up, but your torque drops. On the flip side, if a small gear drives a massive one, the speed drops off, but you get a huge spike in torque. Mechanical advantage is a strict trade-off. You literally cannot have both at the same time, so you have to meticulously engineer for the exact output your machine actually demands.
Now, what's really interesting about this setup is how that trade-off dictates the physical design of the gears themselves. We basically have 4 primary types to work with. Spur gears are your simple, parallel, high-efficiency workhorses. You'll see them a lot in basic gearboxes or conveyors. Then you've got helical gears. Their angled teeth make them incredibly smooth and capable of handling high loads, making them absolutely perfect for car transmissions. Bevel gears take all that power and yank it 90 degrees, which is a total must-have for marine drives and differentials. And finally, worm gears. These give you a massive speed reduction and self-locking capabilities, which, trust me, is exactly what you want holding an elevator safely in place.
But hey, gear geometry is about way more than just continuous, endless rotation. You know that super satisfying clicking sound your socket wrench makes when you're working on something around the house? That's the ratchet and pawl mechanism in action. By tweaking the geometry into these sharp, asymmetrical teeth, the gear allows for rotational movement in just one direction, while the little pivoting pawl physically drops down to lock it from reversing. This kind of specialized intermittent motion is absolutely critical for tools, lifting jacks, and even intricate clockwork where an accidental reverse motion would basically be a disaster.
All right, let's scale things up in Section 3, Driving Cars and Ships, Heavy Duty and Transportation.
When we move to the heavy-duty transportation industry, the core problem gets really intense. To power a massive ship or a car, brute force alone just isn't going to cut it. If you try to apply raw engine power without carefully managing it first, the destructive vibration, the massive torque loads, and the need to violently redirect that power 90 degrees to the wheels or propellers, well, it would literally tear the machine apart.
So the crucial point is how highly targeted gear designs perfectly solve these massive automotive and marine challenges. For instance, we use helical gears in car transmissions because their angled teeth engage gradually. That's exactly why your car shifts so smoothly and quietly on the highway, even under heavy loads. In rear axle differentials, hypoid gears offset the pinion axis, which actually lets engineers physically drop the vehicle's entire center of gravity. And for giant marine propulsion systems, double helical gears use mirrored V-shaped teeth to completely cancel out the immense, destructive axial thrust forces that would otherwise shred a ship's driveshaft in no time.
Let's take it even bigger. Section 4, Aerospace and Renewable Energy, High Stakes and Massive Scales.
135 to 1. Think about that for a second. That is the massive step-up ratio required inside modern wind turbines. You've got these huge, incredibly heavy aerodynamic blades turning agonizingly slowly in the wind, maybe 10 to 60 RPM on a good day. But the electrical generator inside needs to spin at a blistering 1,800 RPM just to produce grid-compliant electricity. Bridging that enormous gap
That is entirely on the shoulders of the gears.
Let's move to and see how this builds into a viable solution for those turbines. Enter the planetary gear system. So instead of just one gear violently grinding against another, you have a central sun gear sitting right in the middle. Then multiple planet gears revolve around it, beautifully distributing that massive, crushing wind load across several contact points at once. The whole thing is then tightly contained within a compact outer ring gear. This brilliant load-sharing epicyclic design is pretty much the only reason wind turbines don't just tear themselves to pieces under extreme torque.
Now, over in the aerospace sector, precision is literally a matter of survival. Just to give you an idea, upgrading to precision spiral bevel gears in a helicopter's rotor transmission can cut the noise down by a staggering 16 decibels. And we're not just talking about giving the crew a quieter ride here. That noise reduction saves vital communication and significantly cuts down on the structural vibration and fatigue that could cause a catastrophic mid-flight transmission failure.
And then there are fan drive gear systems used in commercial jets. This concept perfectly captures how gears solve the ultimate aerospace dilemma. See, in older jet engines, the rear turbine and the front fan were directly connected on a single shaft, meaning they were forced to spin at the exact same speed. The problem? A fan is most efficient when it spins slowly, while a turbine reaches its peak efficiency spinning incredibly fast. By dropping a high-capacity gearbox right between them, engineers effectively decoupled their speeds, allowing both components to run at their absolute peak aerodynamic efficiency.
Which brings us to our final stop. Section 5. Micro-robotics and surgical tech. The micro-future of precision.
When we shrink things down to the scale of microscopic surgery, traditional metal gears actually become a massive liability. They require backlash, which is just a tiny bit of wiggle room to keep them from jamming. They're heavy, and they absolutely need regular lubrication. Obviously, in a perfectly sterile operating room, having a gear dripping oil is a complete non-starter. So engineers developed polymer metal composite gears. These advanced materials absorb vibration, they offer incredible dimensional stability, and crucially, they operate with zero lubrication, keeping the surgical field completely 100% sterile. But the absolute crown jewel of modern surgical robotics has to be the strain wave, or harmonic gear. Honestly, this thing is a total game changer. It delivers massive torque with exactly zero backlash. Zero. It pulls this off by literally deforming a flexible spline inside an outer ring gear as it rotates. This wild design gives a 120% increase in power density over standard setups. And even better, they feature these hollow central shafts, which allows engineers to easily route electrical cables, fluid lines, and suction tubes straight through the center of multi-axis robotic arms.
So, from ancient water mills all the way up to modern multi-access robotic surgery, the applied uses of mechanical gears have been the quiet, heavy lifters of human progress. But it does leave us with a fascinating question. As we accelerate toward a future of frictionless magnetic drives and laser-driven optical microactuators, will the traditional interlocking mechanical gear eventually become a relic of the past? Or will it forever remain the unbeatable muscle of human engineering? It is definitely something to think about. Thank you so much for joining me on this explainer, and keep exploring.